Hello and welcome to our monthly Protocol Engineering AMA. This is Rick, live with JCV, Joshua, and of course our co-founder Max Sanchez. We'll be getting to your questions shortly. We have some from the community already submitted on our Discord channel, and we will be taking more questions during the show. So let me just kick it over to Max and team, and we'll get things started.
All right, cool. Thanks everyone for joining us. Today we're going to be talking about all things Rust, op-reth, ZK provability, maybe, probably. And yeah, so looking forward to getting to questions. A little bit of background to set the stage for anyone who hasn't been maybe following the recent Midweek with Max's or some of our other announcements or work. One of the big initiatives we've been working on is the op-geth to op-reth migration, partly because Optimism upstream is deprecating op-geth or has deprecated op-geth, but also partly because that feeds into some of the ZK provability stuff we need to do, which basically needs guest VMs to be written in Rust that we can then run to ZK prove parts of our protocol. And so we're starting with op-reth and then the shared components that flow over to the Kona stack and then up to op-succinct and Kahlua or our own forks of those that we are now working on building. So those are sort of the two main areas. And then also another big one in our stack, which kind of flows up into op-reth, but was also built for ZK provability of Bitcoin in isolation. So there's some other cool, outside of the HVM use cases potentially for this, but we built it for the HVM as what we call the oxygen indexer, which is also written in Rust. And that is a translation of our current Go TBC deterministic Bitcoin indexer that we can run inside of the EVM to support the HVM precompiles. So Oxygen is a Rust fork of that, that instead of just having sort of flat database indexing, it folds all of the critical Bitcoin state into a Merkle partition tree. And so then that lets us basically authenticate queries against some known state root and also easily ZK prove state transitions from the state tree represented by one Bitcoin block to another in the same way that most people who are building ZK proving things in the crypto ecosystem are used to on the EVM side for being able to prove ZK queries against or ZK prove queries against or state transitions to the Ethereum style Merkle partition tree. So that is a little bit of background on what we're working on and what we're going to be chatting about today. So I'll throw it over. I don't know, John, if you had anything else or Joshua that you wanted to add before we kick it over to questions.
Yeah, I think I'm good. Let's hear what people want to say before we start. Because otherwise, yes, I'm sure I could give opinions on Rust, but they're not all negative, for the record.
We are totally unbiased.
All right. Well, let's get some questions, even though I really do want to hear John's negative and non-negative opinions on that, but I'm sure we'll get to them. All right, from Funky Sasquatch, why did Hemi choose op-reth as part of its infrastructure?
So two reasons. One, we originally started out with op-geth, which is being deprecated by Optimism. And so in order to not have to basically take over the entire maintenance of op-geth ourselves, we do need to transition over to op-reth before the next Ethereum hard fork, or we'd be basically the official new maintainers of the op-geth program, which we're not interested in doing at the moment. So that's part of it. We were already working on some components, sort of a minimal translation or conversion of the Hemi specific changes to op-geth over to op-reth and the broader Rust ecosystem of the Optimism stack for ZK provability. So basically with the deprecation of op-geth, we moved that to, instead of being just needing to get to the point where we had a Rust implementation of the state transition function and the DA block derivation pipeline and being able to glue those together. Now it's a full first-class support of op-reth as a live peer on the node, and then eventually as the primary supported implementation. So we were already working on some of the Rust stuff before for ZK provability, and now with the deprecation, we're expanding it from just what we need for ZK provability for, again, state transition function, the DA derivation pipeline to get blocks from Ethereum DA data, to the additional work on top of that we need to make op-reth basically a full normal node on the network.
And actually, I want to say a little more about why we decided becoming the maintainers of op-geth was not the right choice. Because in one sense, it doesn't sound like the worst thing in the world, right? Like, we're making our changes to op-geth. We are all, we're all Go hackers. We're big fans of the language. It is, in my opinion, and I know some other people on the team have possibly even stronger worded versions of this. I think Go is probably the best general purpose language out these days. Like, I absolutely, and again, general purpose. There are some languages that have uses for other things. Like, if I had to do nothing but statistics all day, I'd use R. If I was just talking to hardware all day, I would probably use C. If I don't know, if I really, really hated myself, I'd maybe go back to Perl. And Max, I bet you thought I was going to throw Java under the bus there, but I didn't.
I was waiting for it.
But, so we like Go a lot. But the problem is, like, if a bunch of us have been on the sort of back end of trying to maintain a fork. And op-geth is a fork of geth. So ultimately, we'd be in a position where we have to make sure we maintain that whatever, goes into geth upstream for Ethereum, but also keep it up with the changes that it would need to keep working with an optimism style code base, and maintain it for our code base, and make sure that, Ethereum's got a hard fork coming out. Are we ready for that? And honestly, that is just more than not only do we not have the team for that, but we'd be able to do it, but that's all we'd be doing. And is that how we want to spend, the limited amount of development time and that we've got? It is a much bigger batch of work. Like, there was a point where I was maintaining, there used to be a patch on Bitcoin for doing address indexing, which is very expensive. It's great if you're running like an Explorer or things like that, but it never got merged upstream because it wasn't generally useful. And I spent a long time maintaining that patch so that it would keep working on newer versions of Bitcoin D. And that was just one patch, and it was a colossal pain in the ass. So to do that for all of op-geth would have been crazy. So, so this is one where swimming upstream was not going to help us.
And we'd be doing all that while maintaining a partial fork of all the critical functionality in versions of the Rust program that we're not using as a node, while we're actively maintaining a geth version of the node that we're not using for ZK proving.
Yes. So all of that put together makes it was a pretty clear choice. So that's why.
It is sad to see op-geth go, though. It is.
I mean, there are flaws, but deep down there are things about geth that I like, and it's not just that it's written in Go, and so it's not just this is a shitty piece of software, but it's written in a good language. No, there are good things about geth. It is a big, complicated monstrosity, but I don't think anyone has ever written an Ethereum-ish client that is not a big, complicated monstrosity.
Yeah, I think by definition, any implementation of the Ethereum protocol is going to be quite a complex code base.
Yeah. And that's even if, because they're the ones that have tried doing it where they just import the, EVM parts from geth. So even if you get rid of it, don't worry about the EVM. And you just think about the peer handling, the message handling, the blocks, everything. You still have a big, complicated mess.
Yep, and maintaining compatibility with changes to the engine API for the consensus layer to drive the execution layer.
Yeah.
There's always, it sounds like a simple thing, but for some reason, there's always something that you have to be really careful about in engine API updates. There's always one little weird gotcha or edge case. So,
when they got rid of proof of work, there was there was a brief shining moment where it felt like, oh my God, maybe this will make Geth simpler. No, I was so wrong on that front.
But doesn't it make sense if you remove the consensus from the client? It must get simpler, right?
It did sound that way. I believe that there was a point, maybe this was when I was up late waiting for, the merge to happen, and I thought it would.
And no.
All right. Still on top, creator asks, how has op-reth improved Hemi's performance compared to the earlier execution layer? And what measurable gains have you seen in production?
So we're not running it in production yet. We're still doing internal testing. We haven't run exhaustive benchmarks. It's generally some of the EVM execution sides are faster, but there's not a measurable performance increase really from op-reth. The kind that could justify like, oh, if we're on op-reth, we can, increase the gas budget 4x or something like that. It is faster, but the main benefit of converting everything over and adopting op-reth is ecosystem compatibility with what's going to be maintained upstream, and then being able to easily plug into existing ZKVM provers and ZKVM infrastructure built around the Optimism stack that's all Rust-based. So it's there's some performance benefits. I mean, there are, if you look at the languages themselves, like Rust will give you, generally speaking, and you can always, with almost every guarantee that Rust gives you as a language, there's a way that you can screw it up, right? But in general, Rust doesn't have a garbage collector of any sort that's running. There's no like runtime under it like you have with Go. And so even if the performance is not all that much faster for a lot of, critical path use cases, and it is a little faster, but it's also more consistent. So, you don't have like micro stutters in, certain heavy computational parts because you're not sure like when garbage collection is going to be executed as part of that. So,
At least
I guess from that perspective,
these days, like
it is good. I mean, it's a, and again, I have not measured this. I'm just going off of like the general design, but I do think you get a little more consistent timing with Reth. But to the point that it matters, no.
Go's garbage collector, like circa Go 1.2 or 1.3, and I wish Marco was here because he would have something to say.
He'd give you like a 20-minute history of the garbage.
There was a point where Go's garbage collector was bad. It was like you would have pauses that were noticeable, not even measurable. Like you could just like wall clock noticeable occasionally. But that was years ago. Go's garbage collector is good, but I mean a little bit. So like, yes, the history of Reth, the way this happened was, there was Geth and it was slow. And people wrote a team wrote Turbo Geth, which became Aragon, which was faster. And then another team, resurrected the idea of an R client after the demise of Open Ethereum. And Reth was supposed to be faster, much faster, actually, to the point that you didn't need snap sync because it could sync fast enough that you would never need to do that. And that was the case very briefly. And then the real world caught up with it. And it ended up that Reth performs very similarly. Maybe a little faster here or there, but Reth is similar to Geth in terms of performance. For a better,
and I'll mention on the snap sync node, one of the things that we lost initially going over to op-reth was the lack of snap sync. So one of the parts of our transition over to op-reth is we've re-implemented the Geth style snap sync in op-reth so we can keep supporting snap sync. A lot of the other, I mean, if you, just as a side note, if you go and do a mainnet Ethereum sync with Reth, which does not support snap sync, so that's kind of your only option. I think when I did it on my machine like 3 months ago, it took 3 weeks, maybe 4 weeks. And that's like a decent machine. NVMe SSDs, like, you know, it's you need SnapSync fundamentally for you know, you can't just host data directories, and especially once we get decentralized sequencing and things like that, like you need, if you want to bring up a node, it can't be a month project to do it.
Even though for a lot of the history of Ethereum and L2s, it was a multi-month project to sync up a
And
node.
still is, yes.
Yeah, it's absolutely, it is absolutely bonkers how much data Ethereum and its various L2s have, and just the amount of time it takes to go through it. It's crazy.
And that's even with blob pruning. So there's just
Yeah.
18 days of blobs, and then what are we up to now? 11 years of EVM state history.
I'm actually super proud that when we used to host a lot of archive nodes, and I managed to kill the physical disk that was backing a couple of AWS instances with that. That's how, like, you know, disk intensive and abusive it was. That my thing went down, spent a lot of time talking with the things, and they're eventually like, no, you killed the real disk, not whatever like AWS presents to you. And it's like, oh, I probably ruined someone else's day too.
Probably the only disk I've ever killed in a cloud environment. Luckily, it was a dedicated server, so there weren't any other tenants. But it was an ETL that I wrote that basically used the SSD as swap space for a blockchain indexer. It was a terrible design. It was
That'll
thrown
do
together in like a weekend. But yeah, I checked the once the drive was like flaky, but you could still talk to it.
Yeah.
I ran the NVMe CTLs, and it was like, I don't know, 10 or 15 petabytes written to it. Apparently that ruins SSDs. Who would have thought?
Yeah, they don't like that. But yes, at least there was a real disk. There was a real actual one. Like, it's not supposed to happen. The cloud's supposed to be magic. You know,
It's not.
Yeah, until you break that magic.
I've had better uptime on dedicated servers than on cloud.
Oh my God! For the longest time, I ran an Ethereum node on one of my machines at home with an array of, not SSDs, an array of spinning disks. Did it as RAID 0, so that, you know, the fastest but least safe way to do it. I was able to keep it up until the disk eventually died.
Oh,
but
I'll take it.
I was just doing it because that was when they said you can't run Ethereum on spinning disk, and I was like, no, you know what?
So of course you had to try.
Yeah, they told me I can't. I'm going to.
How many weeks behind the tip was it though?
No, it kept up.
I'm impressed.
I forget, it was a ZFS RAID 0 of, I don't even remember. It was like every spare, it was however many disks I could fit in the computer. You know, just to give it the most right performance I could get.
Oh, geez.
Yeah, it was not useful, but I wanted to do it.
You proved him wrong.
Yeah, for a while. I kept that going for a good amount of time until eventually, you know, entropy wins in the end.
Damn physics.
Never did anything good for us.
All right, before we get back on the subject of aliens, let me move on to the next question.
How do you know that's where we'd end up?
I saw the slippery slope happening. So, from Peace Wayne, how does op-reth interact with the Hemi virtual machine, and were there any major engineering challenges integrating them?
So the regular architecture is basically you have the REVM, which is a Rust implementation of the EVM, and then op-reth uses that as the EVM execution engine. And so on the Hemi side, if you look at, just forget Rust for a second, what we did on the op-geth side, and then I'll talk about the translation over to it. So on the op-geth side, the Hemi changes that are relevant to EVM execution was basically HVM, which is the added Bitcoin precompiles. And so the actual precompiles are very simple, like the actual code in op-geth that, gets the precompile call and then does something with it. But behind that is a giant custom Bitcoin indexer called TBC. And that's where the real magic happens of indexing all the Bitcoin data deterministically. op-geth, in addition to the precompiles, has to have a little component as part of block progression or consensus, not consensus, but block progression on the main chain that op-geth considers canonical at that point in time. It has to have a component that advances and or when needed reorgs that Bitcoin indexer based on L2 state. And then we also have 2 different custom transaction types that we added. So it's not technically like EVM execution, but it's what's permissible as a transaction type that gets processed by the EVM, which is a POP payouts transaction, then the Bitcoin attributes deposited transaction. The latter of that, the Bitcoin attributes deposited, is what's used to deterministically drive the known lightweight or header-only consensus state of Bitcoin that the Hemi protocol is aware of, and then the execution client that processes an L2 block that has that Bitcoin attributes deposited transaction in it needs to basically validate that the new Bitcoin headers in there are valid, and then add them to its lightweight view of Bitcoin consensus, and then based on that decide how to instruct the Bitcoin full node indexer, which on the op-geth side is TBC, to what Bitcoin block height it should index its state to, and then represent, so that when you do an HVM precompile call, it has that Bitcoin indexer indexed to the correct Bitcoin state that aligns with L2 canonical knowledge of Bitcoin consensus, and thus has a way to deterministically respond to precompile queries. So every Hemi node that's at L2 block 1000, where the view of Bitcoin is, block 12, there's a 2 Bitcoin block delay in the indexing. So all the precompiles will run against a full node Bitcoin indexer that's managed by the execution client that is indexed to Bitcoin block 10. And so basically I had to replicate all of that over on the op-reth side. So from a difficult engineering perspective, most of that's mechanical. It's finding, okay, where are transaction types defined? Okay, let's add our new transaction type definitions. Whereas, what updates do we need to make to the peer-to-peer layer to allow blocks of these new transaction types to propagate? Where are the precompiles executed, and how can we add new precompiles? The 2 harder engineering problems, one of them was self-inflicted in the sense that we didn't need to do this, but as I mentioned earlier, we didn't want to let go of SnapSync, and so re-implementing the SnapSync protocol, which we already made changes to for HVM, because HVM adds some new information to the blockchain that SnapSync needs to be aware of and handle correctly. Supporting SnapSync over, that was again, it is still just kind of one-to-one translation, but that's a larger chunk of fairly complex code. So that was definitely somewhat challenging. And then the more challenging part was, so all of the, execution client side stuff for, precompiles and new transaction types, and, actually managing a Bitcoin indexer was relatively easy. But because, so the current Bitcoin indexer, the Bitcoin full node TBC that's written in Go, and as a sort of transition path, we're using a wrapper around it that allows us to use the Go Bitcoin indexer from op-reth, so we can keep basically compatibility while we transition from every node on the network being op-geth to every node on the network eventually being op-reth. There's going to be a transition time in there where it makes sense to still use TBC as the canonical Bitcoin indexer across both implementations, with a sort of a wrapper around it that makes it callable and manageable by op-reth. But the end goal of this whole Rust conversion project is ZK provability. And obviously now maintenance with what Optimism is going to be maintaining upstream. But the other major motivator is ZK provability. And for that, the architecture of TBC would need to be changed quite a bit to make it efficiently ZK provable. So when you look at ZK, when you're implementing a program that you want to be able to ZK prove state transitions of, generally the best way to do it, and not for trivial programs, but for anything that's managing large amounts of state, like anywhere where you'd have, say, a database on disk, you need some way to be able to fake out that database access and writes to that database in a way that you can cryptographically authenticate. And so, if you just have like the way TBC is built with just a level DB database, you have basically, a table with millions of entries that are all, say for, one of the tables, a mapping of transaction IDs to the Bitcoin block they're included in or something like that. There's no way to easily reference the current state of that database in a way where then you could make changes to it or run queries on it and then prove that that query was run correctly, or that you did a state transition on that database, that you inserted transactions in a new Bitcoin block at the end of that table, and that now the state looks like Y, right? You could have the entire database. ZKVMs don't have disks. There's no concept of like disk storage. With a ZKVM, everything is, you have your virtual processor and you have a very small amount of memory that you can use, basically RAM that the program accesses, and that's it. There's no networking, there's no disk IO. And so anything you need to do either needs to effectively fit in a very small RAM disk, if you will, if you wanted to like just do a one-to-one conversion of something that already uses an on-disk database, it would need to all be in RAM in the ZKVM. Or since that's not practical for an entire Bitcoin indexer or the entire Ethereum state, what you need is to reformat that state into a canonical, reproducible, cryptographically authenticatable structure. And so this isn't necessarily part of this wasn't a requirement to get op-reth working on the network, as demonstrated by us using that TBC wrapper as sort of part of the transition process. But for ZK provability specifically, we needed a Bitcoin indexer that we could run the state transition on its database in a ZKVM, prove that, if you're at Bitcoin block 100 and you index to Bitcoin block 101, your state previously looked like this and now it looks like this. And then being able to then run queries against it, for example, check whether this UTXO is spent. You need to be able to cryptographically prove somehow that you queried the entire database and you either found this result that it's unspent, or this result that it is spent, or this result that it never existed. And in order to do that, again, you can't just have a giant, several hundred gigabyte level DB database, because in a ZKVM, you can't access that. You can't prove anything about that. And so you need a different structure, which is why for Oxygen, which is this Rust translation it's a translation of TBC in some sense. It's a re-implementation of the core features of TBC done with a different data model.
It's a reimagining of TBC.
Thank you. That's a whimsical word. It's a reimagining of TBC, where we're replacing that sort of flat database structure that works fine for what we originally built it for in op-geth without ZK provability, with a system where the entire, all of the important parts, which is like 95% of all the records actually in the database. There's some metadata and like hinting indexers and stuff that you don't need in ZK because they point you to something that itself resolves to something else in the data structure that you can prove in ZK. But anyway, basically taking almost all of the data in the Bitcoin indexer and folding it into a Merkle-Patricia tree in a way that is still reasonably performant for updates. It's always going to be more expensive to put stuff in a cryptographic hash tree than it is to just put it in a flat, row-based database. But not too much overhead, and then be able to then authenticate any query against that data structure with a cryptographic proof, which gives you two benefits. A, once you actually have the data structure, if you want to prove, again, like, this TXID is unspent, Well, there's a certain key you can look up in the Merkle producer tree that's going to map that TXID to a leaf node, and that leaf node is going to tell you the current state of that transaction output, whether it's spent, whether it's unspent, and if it's not in the tree, then it does not exist in the Bitcoin chain up to the state that that tree represents. So you get all three potential options just by using the TXID as a key in the Merkle producer tree and having the leaf always be the up-to-date information about the spend status of that transaction output in the current view of Bitcoin. And then the second part of putting it into that tree is you can prove a state transition between trees representing different points in Bitcoin state. So if you have a tree that's at Bitcoin block 99, it's going to have a certain state root. And then a Bitcoin block at block 100, it's going to have a different state root. And because you can authenticate any subpart of that tree with a jagged Merkle proof, basically, that witnesses that certain data is in the tree or that certain data is not in the tree, you can use that to ZK prove a state transition very efficiently. So what you do is you run the state transition in the clear, meaning just not in a ZK VM context. You're just running the state transition on the full database where the entire tree is stored on your disk. And then you basically trace every part of the tree that's being touched by the update query. And then you pull that out as like this jagged Merkle tree, subsection, if you will. I don't know I'm trying to think of a good like visual analogy for it, but basically you extract a portion of the tree that's the actual parts of it that you're going to query when you're processing a new Bitcoin block. And then you augment that with the surrounding nodes in the tree that are required to reconstruct state. So for example, in a Merkle tree that people are familiar with, you have, every node in the tree has two children, unless it's a leaf node. And so if you're going to prove that, data in this leaf node is part of the tree, then you also need its sister or sibling, or you need the sibling nodes all the way up the tree to reconstruct a Merkle proof. In a Merkle producer tree, it's the same idea, except if you have a radix of, say, 16, for example, there are potentially up to 15 different children that you have to include the hashes of to provide a verifiable proof of certain data being stored in that tree. But anyway, you take that tree extraction, you augment it with those sibling nodes or the hashes of the sibling nodes that you need in order to be able to validate the entire portion of the Merkle tree or the Merkle producer tree that you've carved out that you need to use for the state transition. And then in the ZKVM context, you take that version of the tree and you feed that into what basically mocks out a database that pretends it has access to the full tree. But luckily, since you already were able to trace through this deterministic execution of a state transition on this tree, when you rehydrate a partial portion of the MPT inside the ZKVM behind this sort of MPT abstraction interface, you are then able to run your normal state transition code the way it runs in the clear with just this sort of partially mocked out backend database that only has access to a very small subset of the total tree, which is just what is actually going to be accessed during the state transition. And you don't need to basically implement two completely different proof systems or state transition systems rather, for one to run in the clear and then one to run in a ZK context. So it lets you very efficiently have one version of the code, which is great because for stuff like this, any tiny deviation in how the code works would be consensus breaking because it causes a split where you have the in the clear either able to process something that the ZK one can't process or vice versa. Whereas now you can just reuse the exact same code, and basically your only difference between the program you're running in the clear and the program you're running in ZK is the tiny little bit of scaffolding around it that basically reads in a partial extraction from an MPT, validates that all of the data in the MPT actually does validate to the claim state root, and then puts it into that mocked, again, not mocked, but that facade database backend that pretends it has all the data, and then just conveniently, the only data it's ever asked for is the data that was pre-fed at the beginning of the ZKVM guest program initialization. So that part, not required for op-reth to get op-reth itself working, but for ZK proving that part, we had to, as John put it, reimagine the Bitcoin indexer in a way that we do have this global authenticatable state root that we can then use for, again, queries and state transitions of the entire state of the Bitcoin blockchain, so that we can then run that in a ZK VM efficiently, and thus the entire state transition from normal EVM execution to HVM precompile execution to state transitions of the index Bitcoin view that those precompiles have access to. And then if you want to go up a layer to the consensus side, L2 block derivation from data published to Ethereum DA, that all of that could then be ZK proven, because the one component that is not already well structured for ZK proving, which is the Bitcoin indexer, has now been reimagined into a Ethereum style, in a way, data model for the entire Bitcoin blockchain.
And actually, one thing that I would want to add to this is, to even back a little further, we're all used to computing where you have, in most cases, what feels like unlimited RAM, unlimited disk, until you've run an Ethereum archive node. But otherwise, it's nearly
compiled some Rust code.
Yeah. It's nearly unlimited RAM. It's nearly unlimited disk. You have multi-threaded processors that do speculative execution and all sorts of other messes that you have very little sense of what actually goes on behind most things. So, it's moved significantly far away from the sort of theoretical Turing machine that you learn about at some point for what the model of a computer is. When you're doing it in a ZK, or even like people who, for people who've been around long enough that they did anything with assembly or things like that, where they're still abstractions, because almost everything is an abstraction, but the abstractions seem a little more, closer to the physical. Whereas our abstractions for computers, on your laptop, there's almost no relationship between how you interact with your laptop and how the shit actually happens inside. When you're doing the ZK VMs, you're going back, you've got some sort of VM that, very simplified RISC-V VM. So you need things to be set up so that they work in a much more basic abstraction of a computer. So even though deep down, anything that your computer can do, a Turing computer can do, or a Turing machine can do, the abstractions that you need for it to make any damn bit of sense are very different. So you end up with a simplified and also much more self-contained view of things that you need to make things work in the ZK VM. Even though, yes, deep down, one RISC-V machine versus another, it should be, in theory, the same. But what you can reasonably do in reasonable time with reasonable constraints end up being different. And this makes you, look at things without your, databases that can just write forever, or whatever other, whichever abstraction matters to you has to be wiped away a little. And we have to do something much more basic and simple than that.
Yeah, think of, I'm glad you brought that up, because 2 points. One is, why does everyone use Rust for ZK VMs? And the answer is partly just sort of, that's where it started with, a lot of the original circuit libraries. Halo 2 was implemented in Rust. Plonky 2, Plonkish, I think those are all Rust-based. So there's sort of some language inertia around, and those aren't ZK VMs, those are, you're writing handwriting custom circuits. But that sort of, a lot of that, and a lot of the underlying, math that's used for those was written in Rust. And then, so when you're building out ZK VMs, you already have this kind of rich library of stuff that's in Rust that then you can reuse instead of translating or writing cross-language adapters. But also the other practical thing is, for the ZK VM context, explicitly in ZK VM, there's NARC, which is a Go library for writing custom circuits or defining or describing custom circuits in Go, right? So there's some stuff in the Go ecosystem for ZK. There's some stuff in the Java ecosystem for ZK, but it's much more limited. But when you get to ZKVMs themselves, when you look at the guest programs for ZKVMs, like John was talking about, every bit matters. I mean, modern ZKVMs have enough RAM that, you're not like over optimizing ridiculously small things like you're on some tiny embedded system. But you're much more constrained than you are in a regular resource environment. And more importantly, there's features missing that you don't even think about when you're building, you're writing some Go code. You're not thinking about how the runtime underneath runs, what OS system requirements or, that runtime expects to have access to. And so when you're building a ZKVM, you have to go all the way back to essentially bare metal of, I have a RISC-V processor. There's no kernel, there's no OS. We're just literally loading code onto a virtual chip that has access to some memory, and we're running the program. And so I'm not a, low-level language design guy, so I'm not going to try to do the details justice here. But, with Go, you have a garbage collector that's running on multiple threads. Most, if not all, ZKVMs do not support multi-threading. There's some work now to make it so there's multi-threading supported, not as a performance improvement, but just for better compatibility with things that are written that do use multiple threads that would not run properly on a ZKVM. And that's very complicated because ZKVMs need to be deterministic, and so you need a deterministic thread scheduler that lives inside of the ZKVM that your program runs on top of, yada, yada, yada. There's a reason people aren't really doing that, and it's sort of now just starting as an interesting kind of research project. But for Rust or for C or C++, that's going to compile to a RISC-V binary that you can just run on that bare metal chip versus most other languages. There's obviously exceptions. There's things that compile to native binaries that don't have any need for threading and things of that nature. But for something like Go, you're going to have that runtime under it that's compiled into the binary, and that's more than likely going to use or expect certain things available from sort of a base OS abstraction that are not available in a ZKVM. And that's not to say, you couldn't use something like TinyGo. And again, not an expert on this side, but, there are initiatives for people building ZKVMs that support Go as like a first-class citizen, or, at least Go compiled in a certain way like TinyGo or something like that. But, since Rust is more bare metal, it or, C or C++ make the most sense as a language to target a ZKVM guest program instead
You
of...
just said C++ made sense for something.
I mean, you can run C++ on ZKVMs for the most part, I think.
That's horrifying.
I've not gone and tried.
But
I
actually,
compiled one example program.
Your first part, you brought up one of the things, like when I said that there were good things about Rust or things that I like. That's actually, what those first set of examples you gave, that's what Rust is good at, or what Rust was originally great at, where if you wanted to build some isolated little either cryptographic bit or circuit bit or something like that, or when you think about what Rust started from, where it was Mozilla Servo, where an experimental web rendering engine, where it was trying to do sort of small contained things, and all of the Rust memory safety is great when something contains something sort of security critical, or not. When you're talking about circuits, it's not exactly security. It may be security critical, or it may just be correctness critical. If that that doesn't make any sense, but I'm going with it anyway. But things like that, where you want to reason about what's happening with all of your memory. Rust is great with that, whereas a general purpose systems programming language like Go is a little less than great with that. So that's where Rust originally shined. And so for that stuff, I actually think Rust is a really good choice, where you need to reason about memory, where you don't ever have to use Rust. Rust's unsafe, things like that. Then there's a really compelling reason for the language.
All right, we got a question that just came in through YouTube, and then we can get back to some other Discord ones, time permitting. How much AI are you using in the Rust conversion? How are you going
We're
to make the
using
next fun vibe-coded blockchain? Sorry, there was more.
all good. I thought that was the end. We are using AI a fair amount, but with human review in the loop, so nothing's going to production without humans reading through it, understanding it, and for critical parts of it, not like, scaffolding code or like some peer-to-peer protocol stuff, but anything consensus critical or critical for the ZK provability, having that third party audited. So AI is a great tool, but you got to use it correctly. You got to be paying attention to what it's outputting. You can't go into Claude and say, yo, translate all our op-reth changes, all our op-guess changes to op-reth. No bugs. It's it's a good tool, but you have to be careful how you use it.
And it's also a tool being used by, you've got there's a big difference between having a subject matter expert. So if you have someone who knows about consensus algorithms using Claude to go and write or rewrite in the, whichever it is, a consensus stuff, that's very different than if you have someone who has never done any of this stuff and is using Claude to write it for the first time.
Yeah, Claude's gotten to the point where, I still see it make dumb mistakes or way overcomplicate something and make it hard to maintain. But generally speaking, Claude's gotten to the point where if you give it a very specific plan, very specific, depends on exactly what you're writing, but very specific test cases or a very specific way to validate its own work that it can either compare to, like, if you're translating something, a canonical implementation and existing test cases and then running a fuzzer against both of them, things like that. Or if you're building something new, kind of like the Oxygen Bitcoin indexer, if you can give it, good enough, obviously test cases to compare against, but also a good enough and hardened plan for how to analyze its own implementation from different lenses, from, this isn't the greatest example for Oxygen specifically, but say you're implementing something that, has a peer-to-peer component, or, you're implementing something that is, say, a new transaction type in op-reth. Well, there's going to be the actual transaction type. There's going to be the serialization, deserialization layer. There's going to be the peer-to-peer broadcast treatment layer. There's going to be, depending on what the transaction does, but for stuff like the Bitcoin attributes deposited transaction, there's going to be a piece in the block execution pipeline that's aware of what that transaction means to the protocol and what to do and how to handle it. And so when you're implementing something like that, you have to break it up into tiny little chunks and say, okay, here is exactly how this transaction should work. Here's how it should be serialized and deserialized. Here's some test vectors of good examples that should successfully deserialize, and here's what they should look like once deserialized. Here's examples that should fail deserialization. Okay, then that's one layer. Then you have, okay, how are they going to be, what are the rules for including them in blocks? Do a bunch of examples, test vectors. Okay, how is it going to be, managed over peer-to-peer? Is this a transaction type that peers can broadcast to each other or not? Is it a system-level transaction that only a sequencer can create and other nodes validate as part of a block that is sent over peer-to-peer at the consensus layer? Define what that looks like, define how to construct a chain that violates that rule. Well, not a chain in the peer-to-peer sense, but, what is a example of peer-to-peer message exchange that's going to violate that rule and include one of these transactions? Okay, how do you test against that? And then for like the chain execution side, what are all the rules for what that transaction can change or mutate in system state, or, the execution layers. Why am I blanking on words? I'm on like no sleep. The consensus layer state machine. What are examples of valid and invalid state transitions for what it can mutate in the state machine? Here's test vectors for those. Here's a natural language explanation of how to interpret those and why things are that way, and then how that fits into the broader context of the overall system. So, if you do that and then you review what it puts out, and then you run, for things like where it's a language translation, you can run some pretty robust automatic fuzzing of the Go implementation, which is the canonical reference implementation, and the REST implementation. You have to split up your code and how you're testing it. Well, you can't just run, we do have a EVM fuzzer that runs against the top level daemon, but for this specific task of implementing the Bitcoin attributes positive transaction, you'd want fuzzers at each level of that implementation to be able to run against the equivalent version of that in opguess. So at the transaction serialization, deserialization layer, included in a Bitcoin block layer, trying to fake peer-to-peer messages that maybe should be invalid because either it's serialized or deserialized incorrectly, or it's just not an allowed transaction type over peer-to-peer transport. So I got a little off on a tangent there, but you have to be careful how you use AI. And I'll also say AI is very good at finding human-introduced mistakes in translations too. So if you have a part of, and there's a real-world example of some stuff I was working on, part of I forgot what part of op-reth this was in, but it was, I think, an HVM data serialization, deserialization for a precompile call, if I remember correctly. But the way that I implemented that piece of it on the op-reth side, or really REVM, but collectively inside of what we call op-reth, there was an edge case that could be hit in a different way than could be hit in the Go code. And AI review with the right context, with the right seeding and knowledge around it, was able to find that and produce a test case that demonstrated that divergence and fix it. So you have to be careful how you use AI. We're not going to ship ZK provers to production that haven't been audited by third parties and internally reviewed, obviously. But when you use it properly, I think a lot of the AI tooling has gotten to the point where, again, if you contain it and you review what it's doing, it is a very powerful tool.
All right. Let's see. Well, we knew this was going to come up. It's ZK provability. Okay, here we go. What are the upgrade challenges toward full ZK provability, e.g., HVM ZK provability for fault disputes and broader network verification?
And reminder, we have 3 minutes left.
That's a perfect amount of time for a ZK question. High level, so the roadmap is basically op-reth compatibility, and that by proxy gives us all of the changes we need to the underlying crates like REVM and things that other components that eventually feed up into the Kona state transition system. Then there's some changes we need to make to Kona itself for the data derivation consensus layer. And then that needs to be orchestrated together in a ZK proving environment. Oxygen's essentially done, but needs more review and more testing, and then needs to be audited. So Oxygen needs to be both the state transition of Oxygen indexing new data and also all of the HVM precompiles implemented as queries against that data structure. Those both need to be basically wrapped in a ZKVM guest program and tested and audited. And then all of that needs to be orchestrated together to create. So you have 4 layers of proving. You have the proving of the HVM or the Oxygen index Bitcoin state. You have the ZKVM guest for, I'll back up a little bit. You have 4 ZKVM guests, essentially. There may end up being 5 if we separate things out a little more, but the current models, you have 4 different ZKVM guest programs. One of them is Oxygen indexing new data to the index Bitcoin view. One of them's running any one of the HVM precompiles against that index state that Oxygen maintains that authenticates to a state root that previously came out of an Oxygen index or state transition. Then you have the 2 normal layers that you would with any other EVM L2 that uses Ethereum for DA. So there's the state transition function of the EVM itself, which is going to use both proofs of the oxygen state transition and oxygen precompile queries against the index state tree as part. So the EVM proof is going to use proofs wherever it interacts with oxygen, either for advancing Bitcoin index state or running an HVM precompile. And then you have the fourth layer, which is ZK proving of the block derivation pipeline. So basically proving that a certain blob was published to Ethereum with a witness with a KZG inclusion proof, and then proving the actual pipeline that takes the raw bytes of that, deserializes them, converts them to blocks, verifies those blocks are at least validly formatted, and then runs them in the EVM. So those are the 4 layers we need for ZK provability to work end-to-end on the Ethereum side. And then for HBit VM, there's a few additional layers that we need for proving basically the interplay between Bitcoin, Ethereum, and the Hemi network. And so we need basically we have all of this ZK proving of the Hemi chain itself and its Bitcoin view, but then we're introducing a new upgrade to the proof of proof protocol where Ethereum attestation data is going to be published to Bitcoin to basically prevent against nothing at stake attacks, or a new class that we're calling zero knowledge nothing at stake attacks, which is where you could collude to attack the Ethereum proof of stake protocol with enough staking power and not get punished for it because you're not actually releasing that live chain to the network where there would be enough information and evidence for somebody to slash you. But instead you're just ZK proving that fake alternate Ethereum chain, which does not reveal enough information for you to be slashed, even if you are using 2/3 of the active Ethereum staking power to create a fake network that you keep private that you ZK prove. So that there's a difference in the security model, the economic security model of Ethereum proof of stake from nodes on the Ethereum network running full validation and getting confused onto a fork versus a ZK verifier getting fed false information about a fork. There's a huge difference in the security model because in the ZK context, again, you can't prove, or you don't have the verifier of the ZK proof of Ethereum state does not have enough information in that ZK proof, hence the zero knowledge part, to actually determine who it was of the current Ethereum consensus set that produced this alternate chain, and more so doesn't have enough information to actually reconstruct the fault proof, basically, that normally somebody would produce and send to the Ethereum protocol to slash the malicious validators by proving they signed attestations for 2 conflicting blocks at a certain point in time, or produced 2 conflicting blocks, one of the two. And so to solve that issue, we have an update to the proof of proof system, which is going to publish either the full or a large enough subset, depending on economic parameterization of the Ethereum attestation data, to Bitcoin. And so that needs another ZK proving layer that proves that the Ethereum chain that the Hemi chain is derived from itself has the correct attestations published to Bitcoin as seen by Hemi's HVM-based view of the Bitcoin chain through the auction indexer. So that's one more ZK proving layer. Then we need another ZK proving layer for lightweight Ethereum consensus. And then we need one final meta ZK proving layer that wraps all of those and bundles them in a way where the verifier for each of those ZKVM guest programs can be updated by Hemi consensus in a way that the ZKVM meta guest wrapper program is able to change basically it'd be the equivalent of the CRS for like a Groth 16 proof, but it's a little different with ZKVMs and the way they structure stuff, but basically swap out the prover validity checks for each of those layers of the proof based on a live updated change to each of those verifier configurations from Hemi governance. So that was a kind of a long-winded answer, but basically to get to EVM ZK provability for the EVM side of the tunnel, that's those 4 ZKVM guest programs. Each of those can be run and validated independently in the contract. We may wrap them into one for a little bit of gas optimization. And then on the HBitVM side, there's depending on exactly how you slice it, there's basically 3 additional ZK proving layers that need to be added to it.
All right, we are a little past the top of the hour, so unfortunately, we're not going to get to the other questions, but we can save them for a midweek with Max and handle them on Tuesday if you guys are cool with that.
Are any of them
Um,
like super quick questions, or are they?
I'll kick you one, and let's find out. As op-reth continues evolving, how does Hemi plan to stay compatible while maintaining its own protocol-specific features?
Basically the same as we've been doing with op-geth for, gosh, what, 2 years now, if you include testnet. So, and it's the same pattern basically that op-reth uses to stay compatible with reth upstream. So whenever there's major changes, bug fixes, security improvements, basically adopting those upstream changes and then merging them into your downstream code base, which is easier said than done. The rebases, especially with the amount of code that Hemi's changed from the upstream, whether it be op-geth or op-reth now, is relatively significant, and it's intertwined into obviously fairly important parts of the protocol for what constitutes valid or invalid transaction data, EVM progression, how the precompiles work. So there's a fair amount of work in doing those rebases, but it's basically for op-reth, we'll just be doing the same pattern we've been doing for maintaining op-geth and op-node with the Hemi-specific changes with upstream.
All right. Well, we only have one more question. Technically, this would be a yes or a no. I
Let's
just
see.
it won't be,
Yes, and let me
but
tell
it
you
could.
why.
Are there any protocol upgrades or performance? What the fuck is? Are there any protocol upgrades or performance optimizations planned for op-reth on Hemi later in 2026 that the community should watch out for?
Probably not too much on the performance side, other than if you consider SnapSync a performance thing, which I'm sure we could argue all day whether that's performance or not, but the reality is it lets you spin up nodes relatively quickly. As far as features, though, absolutely. So not in any specific order, but we're adding more features to HVM with the ordinals indexer that Mark was working on, and then folding that work into Oxygen. There's going to be, once we get to fully transition over to op-reth with the Oxygen Bitcoin indexer instead of TBC, that lets us enable, that unblocks all of the ZK proving stuff that we want to do, because there's no longer some nodes on the network that have a version of the Bitcoin indexer that doesn't produce these ZK compatible data structures. So ZK provability, and then that means ZK settlement on the Ethereum side of the tunnel, and then with those additional ZK layers that we'll be building out the HBit VM side of the tunnel or the HBit VM tunnel on the Bitcoin side. So those will be large feature improvements. This isn't on the daemon side. This is an application that lives on the Hemi protocol the same way like anyone else could deploy their dApps, but it's still core to like the infrastructure and the product that we're building, is what we've been calling codename Minerify for now. I think the new maybe final name is Fast Track, so I think I'll start using that, and hopefully it doesn't change again. But Fast Track is going to be basically a liquidity wrapper around the Bitcoin tunnel, which becomes even more important once you go to HBit VM, because there's limitations to the size of deposits and withdrawals that you can do with the HBit VM system. They're basically all of them have to be large to justify the economics of constructing the entire Bitcoin transaction graph with covenant emulation, and then actually, in the worst case, the protocol having to essentially pay or have enough incentives to pay out somebody to execute the very expensive fault dispute transactions in that Bitcoin transaction graph if an operating system misbehaves or whatever. So the fast track system, my point was the fast track system is there's a thing flying around, is a liquidity wrapper around the Bitcoin tunnel, which with HBit VM becomes more important, but also just lets people onboard and offboard Bitcoin much easier. And then we're composing that with some other DeFi components that we built to create what we're calling the Hemi Earn protocol, which is a sort of one-stop shop for earning yield on Bitcoin, in the future, maybe other assets, but it's Bitcoin focused from the beginning, where the user flow is basically you go to Hemi Earn, you have a MetaMask wallet installed, you register or set up, which basically reserves a dedicated Bitcoin address in the system for you. And then any Bitcoin that you send to that address automatically gets credited to your EOA that you did the registration with, automatically gets composed into DeFi and starts earning yield. And then, if you're, say, on a mining pool, you can configure that Bitcoin address as your withdrawal, and every day Bitcoin streaming into your Hemi Earn staking account and into yield strategies. Or if you're a trader and every week you want to withdraw a bit of Bitcoin to put it to work in DeFi, you can have that fixed Bitcoin deposit address. You don't need to go through a complicated tunneling process to bring assets on chain. And then you can just set it and forget it, and then come back whenever you want to collect the yield on it, withdraw, change strategies, whatever. So that's it's not protocol related, has nothing to do with op-reth or op-geth, but that's going to be another EVM application layer DApp that people can use that automates Bitcoin yield, makes the entire Hemi ecosystem a lot easier to use. And we have other stuff coming too, but I think those are probably the highlights, and we're already 11 minutes over, so we will get into some more specifics on midweek next week.
All right. Well, that does bring a conclusion to our op-reth monthly AMA. Our monthly AMA, with the topic being op-reth. We don't talk about this every month, but next month we'll have a different subject. You can catch us every Tuesday live right here on YouTube, Twitter, to a lesser extent LinkedIn, for Midweek with Max at 11 a.m. EDT, and Protocol Engineering office hours Wednesday at 11 a.m. Also, there is a Built on Hemi series hosted by Jeremy Nation coming out tomorrow. I believe it's at 3 p.m. EDT. There will be announcements regarding that across our socials, so keep a lookout for that. I just want to thank everyone for joining us. Let me turn it back over to the team for outros, but we hope we see you in the next one. Please join the Discord. Get the builder role, get the beta tester role, and start testing all the cool new Hemi features we have coming out, and join our great community. All right, over to you guys.
All right, awesome. Thanks everyone for joining us and listening to us ramble for an hour about Rust, op-reth, and ZK provability, and whatever irrelevant topics we were running into like at the 20-minute mark. So thanks everyone for coming out. I hope to see you on midweek or the open office, the protocol engineering office hours. Dang it, Rick.
It's not that easy. I'm telling you, I'm getting better.
You ruined it, Rick. You're the reason we can't say that.
Open office.
I think we said we were going to rename it to just engineering office hours, if that makes it any better.
That makes it a little easier. It's one less word.
Yeah, it's a
three less
little
syllables,
less.
so sure. But yeah, join us next week, Tuesday, for Midweek with Max as usual. Wednesday is going to be the first day that, as Rick mentioned, we're moving the engineering office hours from Discord over to this platform as well. So join us there if you are building something in the ecosystem, want to ask questions, chat through, how you're designing a DeFi protocol, or how to get specific data from the Hemi blockchain for a dashboard you're building, or whatever it is that you're working on, or if you just want to hang out and hear people talk about stuff that they're building and what they're working on. And with that, we will see everyone next week.
Thanks, everyone.
Cheers.